Okay, so this video is about the structure of benzene, and I'm going to tell you exactly what you need to know for the exam questions. Okay, benzene is an aromatic hydrocarbon. Okay, an aromatic hydrocarbon. It's the simplest aromatic hydrocarbon. It has the molecular formula C6H6. Okay, that's the molecular formula. So these are the bits that you do need to know at the moment, okay? Molecular formula. Now, when it was first discovered in the 1800s, so you don't actually need to know this, that's why I'm not writing it down. It was first discovered in the 1800s. They knew it was C6H6, but they couldn't work out what the structure. And it took them ages. It took them about 40 years for a German chemist to come along, called, his second name is Kekulé. So this is what you need to know. So he's a German chemist and his name is Kekulé. And in about 1865, he proposed a structure for benzene. He said that benzene is alternating single and double bonds, okay? So it's a hexagon with alternating single and double bonds. So if we were to draw out a carbon, alternating like this, okay, and there's one hydrogen on each carbon, and there's a double bond, single bond, double bond, single bond, double bond. Okay, so here we've got what type of formula? This is called a displayed formula, and this is called a skeletal formula. Okay, so he proposed that, but there was a problem, because there were three key pieces of evidence that disproved Kekulé's model. So when you hear about the Kekulé's model of benzene, this is what he proposed. So this is Kekulé's model. Okay, and there are three key pieces of evidence that disprove this. Okay, and this is what you need to write in exam questions. So there's three key pieces of evidence which disprove his model. Yeah, which disprove the model, which disprove Kekulé's model. Okay, sorry, it took me a while to write it. Kekulé's model. Okay, so the first one is that if benzene has carbon-carbon double bonds, then it should react with bromine water. Okay, so benzene should react with bromine water if it has alkene. Yeah, so if benzene has carbon-carbon double bonds, then it should react with bromine water, because that's the test for alkenes. It decolorizes the orange bromine water, so it should react with bromine water. Okay, so then when they tested benzene, they found that benzene does not react with bromine water, does not decolorize bromine water. So benzene cannot be a alkene. So benzene does not react with bromine water, does not decolorize bromine water like what alkenes does. Therefore benzene does not have carbon-carbon double bonds. Benzene does not have carbon-carbon double bonds. So that's what you need to know. But just to add a little extra, which you don't actually need to know, Kekulé then proposed a reason why it didn't decolorize bromine water. So he proposed that there was an equilibrium in place, a rapid equilibrium, where the carbon double bonds were moving around and moving into a new position. and there's a rapid equilibrium, and that's why bromine couldn't react with benzene. Anyway, so that's one of the key pieces of evidence. Benzene does not decolorize bromine water because it doesn't have carbon-carbon double bonds. Now, the second piece of evidence came much later, in the about 1920s, with X-ray diffraction. So using X-ray diffraction, they were able to measure the bond length, the carbon-carbon bond length. And they discovered that in benzene, the carbon-carbon bond length, is constant, doesn't change, yeah, is the same. And this is using X-ray diffraction. So this is using X-ray diffraction, and it happened, like I said, in the about 1920s. X-ray diffraction. Okay. Now you don't need to know the figures. But you do need to know that the carbon-carbon bond length in benzene is intermediate. In benzene is intermediate between the carbon-carbon double bond and the carbon single bond. And you don't need to remember the figures. Carbon-carbon bond is approximately 0.15 nanometers in length. The carbon-carbon double bond is about 0.13 nanometers in length. And the carbon-carbon bond length in benzene is approximately 0.14 nanometers. Okay, but like I said, you don't have to remember those figures. All right, so you don't have to remember the figures. You just need to know that the carbon-carbon bond length is constant, and it's intermediate between the double bond and the single bond. So Kekulé's benzene would be a short double bond and a longer single bond. A short double bond and a longer single bond. And then, okay, you can see I've not done this very well, because now there's meant to be a short double bond, but it doesn't actually work. Yeah. Whereas what they discovered was that the bond length, the carbon-carbon bond lengths in benzene were all exactly the same length. Okay, that's the second piece of evidence. The third piece of evidence, which also came a bit later, is about the enthalpy change of hydrogenation. Can I just make a comment here? So in exam questions, enthalpy change of hydrogenation. In exam questions, students, oh sorry, let me finish this before I speak. Oh, that's rubbish. Let me rub that out. Enthalpy change of hydrogenation. Enthalpy change of be careful your spelling, hydrogenation. Now, in exam questions, students say, oh, it's hydrogenation, or they say it's enthalpy change, and then they don't get the mark. The piece of evidence is about the enthalpy change of hydrogenation, right? You've got to say both in order to get the mark. Okay, so let me give you a bit of background information here. So if you take cyclohexene, and its enthalpy change of hydrogenation, you've got to say both for the exam question. So you add hydrogen, yeah, and then that will give you cyclohexane. The hydrogen will add across the double bond, and that enthalpy change is minus 120 kilojoules per mole. All right. Now, if you take Kekulé's model of benzene, which is 3 alternating double bonds, then that's going to need 3 hydrogen molecules in order to form cyclohexane. So that means the enthalpy change of hydrogenation, you need that for the mark, is going to be 3 times minus 120, which you can work out as being minus 360. Okay, it's minus 360. But when you take benzene and add 3 hydrogen in order to get cyclohexane, the enthalpy change of hydrogenation is less exothermic. It's actually minus 208. Yep, minus 208 kilojoules per mole. Okay, you do not need to remember these figures. You just need to know that the enthalpy change of hydrogenation of benzene is less exothermic, less negative than it should be, than Kekulé's model. Okay, it's less exothermic. But let's see if we can understand why. But you don't need it for an exam question. Now this goes to looking at bond enthalpies. You can see this on the bond enthalpy video as well. Okay. Now when we've got a reaction on the right hand side, we've got bond making on the right hand side. Yeah? All the bonds are made. And you should remember that bond making is an exothermic process. Yeah. And then on the left, everything we've got is bond breaking on the left. And again, in the bond enthalpy video, you should recognize that bond breaking is an endothermic process. Okay, so if overall, benzene is minus 208, it's not as exothermic. Okay, so let's just think about this. So the Kekulé's model is minus 360, but benzene is actually minus 208. That and this number here, this is the same because the same thing is being made. So this bond making is the same. The only difference must therefore be on the left hand side. So if there's less energy released overall with benzene, then more energy must be needed to break the bonds in benzene. Okay, so benzene has more stable carbon-carbon bonds than Kekulé's model. So that's something else you need. Can I squeeze that? Enthalpy change of hydrogenation of benzene is less exothermic because the benzene is more stable. Yeah, benzene is more stable. The bonds are stronger. It's more stable. It's harder. More energy is needed to break the bonds. Yeah, because this number on the right is the same for both. So it must be the number on the left. That's the same. So it must be, this must be more positive for benzene. Okay. Anyway, you don't need to explain it. You just need to say benzene is less exothermic than Kekulé's model, the enthalpy change of hydrogenation, because benzene is more stable than Kekulé's model. Right, those are the three pieces of key evidence. So therefore, what is the structure of benzene? Yeah, what is the structure of benzene? So let's do a quick bit of revision, because it really helps to do a quick bit of alkene revision first. I know we're talking about benzene, but it really does help to do a quick bit of alkene revision. Yeah. So if you take cyclohexene, for example, yeah. So cyclohexene. Okay, that's my drawing. Sorry, I've all gone crazy all of a sudden. Cyclohexene, which is meant to be a hexagon. Okay. Now, do you remember with what you've got in the structure of an alkene? You've got a sigma bond and you've got a pi bond. Yeah, I am drawing the skeletal. You know, please bear in mind that there are 2 hydrogens on all of those carbons, and there's 1 hydrogen on there. On the double bond. Okay, so I am drawing the skeletal. So remember that all the bonds in an alkene are sigma bonds. Yeah, you just need to watch the alkene video if you're not quite sure about this. Then there's a p orbital, the pz orbital. Okay, and that overlaps, a sideways overlap, which overlaps above and below the ring. And so you have an overlap above and below the ring like that, and that is your pi bond. So that's the pi bond. These are the p orbitals, 1 on each carbon, which overlaps above and below, and that generates the pi bond. Okay, so that's what happens in an alkene. Now when you take benzene, okay, so just put it on a clean page. When you take benzene, okay, again, benzene is, I'm going to draw it bigger. Okay, let's have a look. and this is again, I'm drawing the skeletal. So benzene is a hexagonal structure. Okay, benzene is planar, so it's flat. Yeah, hexagonal and planar. Benzene is cyclic. Okay, and don't forget that there is a hydrogen. Okay, third time lucky. Come on, Sarah, you can do it. Let's draw the carbons and make it nice and clear like that. That's the whole point, to make it clear. All right, there is a hydrogen on each carbon. Okay, and what's the name of every bond that we've drawn here? So every bond so far is, every single bond so far is a sigma bond. Okay, a sigma bond. Okay, on each carbon, like an alkene, on each carbon there's a p orbital. Okay, remember carbon has got 4 bonding electrons, 4 outer electrons. So carbon has got 1 electron in that bond, 1 electron in that bond, 1 electron in that bond, and has a free electron. Yeah, so and that free electron is in the pz orbital. And like I said, it might be worth watching the alkene video if you're not sure. Okay, so there's a p orbital on each of the carbons. Yeah, and the p orbital overlaps above. So there's an overlap above the lobes, the top overlaps, and then the bottom. Oh, this would be good. Colors would be good here. I should have used a different color. Yeah, so you have the planar hexagon carbon ring, and then you have overlapping at the top, make it a little bit thicker, overlapping, and then you have overlapping at the bottom as well. Yeah, so overlaps above and below, but it is 1 pi. It's like an enormous pi bond, a pi ring. Yeah, there are 6 pi electrons. Okay, because each carbon puts an electron in, shared between 6 carbon atoms. Shared between 6 carbon atoms. Okay, and what's the word that we use for those pi electrons? Those pi electrons are delocalized. Yeah, and every exam question about benzene, you've got to put the word delocalized in there. So delocalized, when electrons are delocalized, it just means the electrons are shared between more than 2 atoms. So there's 6 pi electrons shared between 6 carbon atoms, and therefore we actually draw benzene because it's a ring above and below. So we draw benzene not as Kekulé structure, but as a ring like that. It's overlapping above and below, 1 pi ring, 6 pi electrons, and it is delocalized. I hope you found that helpful. Thank you.